So far, we looked at the BM25 scoring mechanism that primarily relies on something known as term frequency. That is, how frequently does our input word appear in the document? The question is, does term frequency always work? In particular, let's take an example of websites. Say, for example, we are searching for the keyword IBM, and what we would like to do is when somebody searches for this keyword IBM, we want to make sure that IBM's home page, that is this page, appears on top. And even we want this to happen even if, let's say, there is another page, let's say a spam.com, another website, where IBM is mentioned very frequently. So if we were to use something like a BM25 scoring mechanism, then because this page has IBM more frequently, we probably will end up ranking this page with a higher score. But what we would like to do is not have that, because obviously IBM.com is a more sort of relevant match to what we are searching for. So in other words, we want to minimize our dependency on the term frequency. One solution for this is to check something known as inlinks. That is, one new idea that we can come up with to resolve this problem is to check for inlinks. That is, say for example, this IBM.com website is mentioned in many pages. Let's say page 1 has a hyperlink that takes you to IBM.com. Let's say we have page 2, another page that has hyperlink that takes you to IBM.com. Similarly, you have page 3 and so on. So we may have a lot of pages that point to IBM.com. Now this is a spam website, so we will probably not have many pages that point to the spam.com because it's a spam website, right? So then the idea is, if we simply check for the number of inlinks, that is, the more inlinks in a page, the more likely that it will score higher. In other words, what we're looking at is we are sort of gauging, checking the reliability of a page by counting the number of inlinks. Now, this is still could have a problem. Here's where this idea could go wrong. Say, for example, we have a really a group of people who are trying to redirect the search to pages of their choice. Then what they can do is create a network of pages, P1, P2, P3, and so on. And what they can do is link all of these pages to each other. Link P1 to P2, P1 to P3, P2 to P3, and so on. So what they have is basically, since this is a network of pages, all the pages will have high number of inlinks. In other words, spammers could create a network of pages and have them all point to a page of their choosing. They could have still a network, and this network could choose a page of their choice. That way this page will always have very high number of inlinks. So this even does not solve the problem. So what we saw is term frequency is not a great idea. Counting number of links is also not a great idea. Basically, what we would like to do is solve this problem of tyranny of scores. That is, this over-reliance on term frequency scores is a problem. And the PageRank algorithm is designed to solve this problem. So this algorithm was designed to solve this problem of over-reliance on term frequency scores. So the core idea behind PageRank algorithm is that you weight the links from high quality sites more heavily. So we still count the inlinks, but what we do is give higher weight to inlinks from high quality sites. So then the question is, what is a high quality site? How do we measure that, right? What is a high quality site? The answer is, a high quality site is the one that is linked to by another high quality site. It's a very funny definition, but it's a recursive definition. That is, something that drives the quality of the web page is the quality of the pages that link to it. So because it's a recursive definition, the page rank of a page can be computed by a iterative procedure. That is, we will start with all pages. So when you are implementing the algorithm, this is what we can do. Start with all pages having rank of 1, and then iterate the algorithm, updating the ranks until they converge. So we can write a for loop or a while loop to let it converge after certain iterations. This is the equation for expression to calculate page rank for a page. The constant damping factor D and N usually don't play a big role in calculating page rank because they almost are constant for all the pages. So these are almost constant for all the pages. And this D is a damping factor. We'll talk more about that. But the key here is this part. And this is for all the pages that link to it. So let's take a look at an example. And before that, we will discuss the equation and then look at an example to see how we can calculate page rank. So say we are given a number of web pages, n equals 3. So I'm given pages A, B, and C. And the damping factor parameter is 0.7. So my D is given to me as 0.7. We would like to calculate the page ranks of the pages A, B, and C. So let's look at this equation. Here in this equation, page rank for any page P, this could be A, B, or C, is given by this expression. Here, PRP, this is the page rank of the page P. N is the total number of pages in the corpus. In this case, n equals to 3. Now, this is very tricky. The INI in this page here, which is referred here and here, INI, are the pages that link in to P. So if we are talking about the page rank of page A, then I would be C. So this I that we have here refers to a page that links to P. So all the pages that have connections that take you to this page will be your page I. So page rank is the sum of all the this expression for all those pages. So CINI is the count of the total number of outlinks on page INI. So say we are talking about page A and we want to calculate page rank of page A, then CINI, if I is C, because C is a page that links to A, then CINI is the count of the total number of outlinks on page INI. So here CINI would be 3 because C has 3 outlinks. And this D is the damping factor constant, usually 0.7, 0.8, or 0.85. Overall, this picture shows how page rank scores look like. Here we have a page B. So this is a different network, very different from what we have, totally different example. And we have a lot of pages that link to this page B. We have page D, another page, E also links to, C also links to F, and so on. So we have so many pages linking to this page B. For that reason, the page rank of this algorithm, of this page will be extremely high because there are too many pages that link to this page. Similarly, we have another page E which also has many inlinks, and this page also will have a very high page rank. Now, what this damping factor D does is, so this page links to E, and because E has many inlinks, and there is an inlink from E to B as well, this score that this page has carries over to E and then to B. So damping factor sort of, here you multiply by 0.7 and then you multiply by 0.7. It damps off the effect from networks that are very far away. So now for this particular example, let's calculate the page rank. So let's just start by trying to calculate the page rank for page A. So page rank for page A will be given by this expression. We have 1 minus D is 0.7 by 3 plus, and what we do is we multiply by this damping factor 0.7, and we look at all the inlinks. So how many inlinks do I have? How many pages link to A? So we only have one page that links to A, which is page C. So then we sum this for all the pages. Since we only have one page, so we don't need to really sum. So this means we will look at the page rank of this page C. This is page rank of the inlink, page rank of this page C, divided by the outlinks of this page C. So this will be 3. So this is our expression to calculate the page rank of A. Notice that page rank of A depends on the page rank of C here in this expression. All others are numbers. Now let's look at the page rank of B. So page rank of this page B will be equal to the same constant plus my damping factor 0.7. Now I will look at all the inlinks to B. So there is only one page that links to A. So this will be page rank of A divided by the total number of, the outlinks of A is only 1. So this will be 1. Similarly, the page rank of C will be page rank of C will be equal to the same constant plus my damping factor 0.7. Now what I will do is I will look at all the pages that link to C. So the number of pages that link to C, there's only one page that links to C, which is this page B. So then this becomes the page rank of my page B divided by the number of outlinks of B, which is also 1. So what we have is a set of linear equations, and we can have these expressions, and once we have these expressions, we can write a for loop or a while loop that runs for maybe 10 times or 100 times, and we can start by assuming that initially the page ranks of all the values, all the pages are 1, and then continue to iterate and iteratively obtain more accurate and more finer values.